Okay, so we are back. Lecture 2 is going to be focused on earthquakes and different type of historical earthquakes and the plate interaction that was the result of the plate movements. We defined the focus point being the spot along the fault where the earthquake waves originate. This is going to be underground. And then we have the epicenter, which is at the surface directly above the focus point. And that's going to be two key points when talking about earthquakes. Now, how we actually identify where the epicenter takes place is we use geologic sensors all around the world, and we're able to, based on the seismograph stations, we're able to triangulate to determine where the actual epicenter takes place. And so when you are completing the virtual earthquake assignment, you're going to be able to determine where approximately, given types of seismograph data that's coming in, where actually the epicenter is located. Now, when we have an earthquake, there's two different types of scales that describe the damage of an area from the earthquake and the intensity from the plate movements, from the waves. The first scale is the Mercalli scale, and this measures damage to the terrain and the structures. And so it's most useful in areas of large populations. And then we have our moment magnitude scale. And so this measures the fault slippage, the surface rupture, and the types of material that are faulted. So when we talk about our Mercalli intensity scale, it goes from 1 to 12, and 1 being not felt, 2 being felt only by a person at rest, 3 to 4 is felt by a person indoors only, 5 to 6 is felt by all, 7 people run outdoors, so on and so forth, all the way down to 12, where damage is total, the waves seen on grounds, objects thrown into the air. So pretty intense. Now, what causes the damage? So we refer to the type of waves that are produced when two plates are interacting with each other as seismic waves. So these two types of waves are identified as the primary wave and the secondary wave. Now, the primary wave, when the plates start to slide or subduct, are referred to as the compressional wave that arrives first. Okay, and then we have the secondary wave, which is going to be the shear wave, so that moves the ground up and down. And you can see on the diagram that we have here, we first have the compressional wave where it's a jolt, and then you have the secondary wave, which actually looks like the ground is moving up and down. For those of you who have experienced earthquakes, boy, I remember when I was in middle school and we felt an earthquake up in Northern California, one of the earthquakes that happened on the coast, and you could see the actual waves as a result. So we could actually see the secondary waves of the ground moving up and down. It was very impressive. So in talking about some significant earthquakes that we've had in the past, probably one of the most famous earthquakes on the West Coast is the San Francisco earthquake of 1906. This is where 300 miles of the San Andreas Fault ruptured, and as a result, it was a 7.7 magnitude earthquake. So pretty significant damage as a result. We can see that buildings were completely moved off their foundation, as an example of the Valencia Saint Hotel. We see entire destruction of neighborhoods. We can see that the streets are also buckled as a result. We also see that fence lines, this would be an example of where we have the individual lateral faults taking place, where the fence line is completely been moved forward, and as a result, the farmer has kind of patched the fence. And we also see parts of the road representing the effects of this kind of lateral movement as a result. So these images are from a report that was created as a result of this earthquake to document the types of damage from this particular elastic rebound result. And this is in a report called the Lawson Report, which is available online at usgs.gov. So by going out and collecting the data in this Lawson Report, the scientists were able to compare data geographically and was able to make to infer the fact that the faulting and movement was along the San Andreas Fault that created this particular earthquake. And we can see that this simple map that we have here, we have the San Andreas Fault, we have the Hayward Fault, the Calavera Fault. So 3 significant fault lines that run through a highly populated area. We also had the large earthquake of 1989, Loma Prieta earthquake, which is a 7.7 magnitude earthquake. This one had a very deep focus point, so being about 18 kilometers under the surface, with the epicenter directly above. The fault shifted laterally and vertically. So Loma Prieta earthquake had a significant impact in the Bay Area because of the high density of population. So similar damage. This is looking at a similar fault characteristic that we see mirroring the San Andreas Fault, but it's not in California, it's in Turkey. So the Anatolian Fault system in Turkey is another example of the strike-slip fault, very similar to the San Andreas. So we can see that the fault can be identified as having a lot of stress and tension from the plate movements. And then we can see that when the fault slips, that stress and tension moves, that energy moves and is released. We also have a significant earthquake that happened in 2010. This is the Chilean earthquake. This occurred just offshore of the boundary of the Nazca and South American plates. This was as a result of this movement, these plate movements, this was a 8.8 magnitude earthquake that lasted over 90 seconds. And so there was over 800 casualties. And it actually moved the city of Concepcion over 3.4 meters to the west. So physically moving due to the plate interaction. Typically after earthquakes or as a result of earthquakes, we have major impacts on the landscape. We have landslides, we have subsidence, we have ground ruptures, we have liquefaction of soil, where the soil is shaken to the point that it almost becomes liquefied and it can flow and move similar to water or rivers. So it has a hydrologic influence, fluvial effect. And also we see tsunamis created as a result of ground being pushed up, so more area being added to the surface basin, or then subsiding. And so that's creating a ginormous wave that we know that can travel across ocean basins. So liquefaction occurs when we have wet soil that's shaken and the soil particles are suspended in water. And these are common in areas such as landfill soils. A lot of San Francisco and even New York is created as a result of filling in the area with soil to make a suitable location to build a city on. We also see that liquefaction occurs in places where there's a past glacial sediment. And I'll be sharing a video shortly about liquefaction that takes place in Norway. Landslides are very common. You hear typically of some sort of volcanic activity that's taking place upstream. And as a result, there are mudslides, landslides that take place hundreds of miles away from the actual epicenter. And you hear of entire villages that have no warning and are completely buried in mud as a result. We also have subsidence, which occurs when one fault drops down to sea level, and this was the case that took place off the coast of India. We have ground ruptures that are also documented historically along the San Andreas Fault and other areas that can be visibly noticed on the landscape. So when we look at subsidence taking place and the movement of one plate dropping down over the other, we know that as a result of this motion, we have this fault block that occurs. And when we have this movement, vertical movement between these fault blocks, the water column becomes displaced. So the water column pushes up, and that's going to be causing a large volume of water as a result. So past historic tsunami incidents took place in Crescent City in 1964, where there was a huge 9.2 magnitude earthquake that struck offshore near Anchorage, Alaska. This was a significant earthquake for this region of the world. I mean, just looking at the devastation, cars, entire roadways destroyed. But as a result, this earthquake generated a large tsunami that traveled south and struck the west coast 4 hours later. And so the waves were 21 feet high, and it struck Crescent City, and it inundated the town, and it killed 11. And but over 100 people passed in Anchorage and Oregon. Now, as a result of this particular earthquake, the entire West Coast has a series of tsunami warnings, and they, particularly looking at Arcata and Eureka, Crescent City, there are now delineated areas for tsunami escape routes. So maps that show you exactly, what elevation you're at, what elevation you need to get to when you hear the sirens for tsunami warning. Other significant tsunamis as a result of earthquakes took place in 2005. This was a completely devastating tsunami that occurred in Sumatra and Indonesia, when there was vertically a displacement of 4 to 5 meters. And this is the tsunami that completely, destroyed 200,000 people in the region surrounding the Indian Ocean. So very devastating result of the plate movements. We even have in our kind of neck of the woods, there's a series of fault lines in Nevada. And when my husband and I were living there, we had a certain flurry of earthquake recordings and lots of shaking that was taking place in 2008. And as a result of Nevada being a very mountainous area, we have lots of faults. So those faults are significant and create the basin and range terrain that we see. Just by looking at the topography of the state of Nevada, there's a lot of mountain ranges that run vertically from north to south. Now, along those mountain ranges, there's a fault for each one, and we call that basin and range. And the types of faults that were creating these clusters of earthquakes, we refer to as normal faults. And so on any given day, we would have 1 to 2 to 10 earthquakes, and it was actually pretty significant. I was teaching physical geography, and the lab classroom was in the basement of the building. And so typically when we were talking about earthquakes, we would actually be able to feel earthquakes, and we would run over to the geology department and look at the seismograph to see what it was on the Richter scale. Okay, so that was a very brief kind of overview of the results and different types of historical earthquakes. So I'm going to go ahead and start moving on into the next topic of this week's discussion. So you'll be able to have the review on the study guide.